Well, good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is our people, are at the core of our success. Today's webinar is titled Development and Verification of a Pipeline Systems Surge Screening Tool using Deep Learning Technology. Surge analysis is a key consideration for pipeline design and construction. Industry insights demonstrate severe consequences in neglecting or overestimating the associated surge pressures and forces. This presentation explores the fundamental mechanisms and underlying limitations of current surge analyses, primarily lack of simulation data. In this demonstration, machine learning is used to forecast surge outcomes based on a provided simulation dataset. The machine learning model is then verified for accuracy and consistency. Surge concerns often arise during the early stages of system design, but comprehensive transient modeling of all pipeline sections and subsystems at this stage is impractical due to the absence of detailed design information. Machine learning models can provide a guide and predict surge outcomes whilst reducing time required for analyses. While not yet adopted in commercial practice, this approach presents a technically viable pathway for early-stage surge assessment. Its potential merits warrant further exploration and validation to determine its applicability within real-world engineering workflows. Now, to set the stage for today's webinar with the HSE topic, please join me in welcoming Caroline Kaza.
Thank you, Dave. Today's safety topic is data security in AI. First, I will go over what AI, machine learning, and deep learning are. AI is a broader field that involves problem solving and includes both machine learning and deep learning. Machine learning is a subset of AI that involves machines learning from data provided and is usually used to do a specific task, like predicting. Deep learning is meant to mimic the human brain to perform tasks, and it involves more complex patterns within the data and is usually used with more complex equations. One of the main concerns regarding AI is the security aspect, since AI is vulnerable to leaking data. One example is Samsung and ChatGPT, where people at Samsung put in confidential code and ChatGPT stored that data to train itself. This meant that OpenAI, the company who owns ChatGPT, now had access to the data and any confidential material it may have contained. As a result, Samsung banned the use of ChatGPT and other forms of generative AI. Another example is when Microsoft accidentally leaked 38 terabytes of private data, including the personal backups of 2 employees' computers and passwords to Microsoft services. This was discovered by a security firm who discovered the overtly permissive sharing permissions. As a result, Microsoft fixed the permission issue and expanded this secret spanning service on GitHub, which is what they were using in that leak the information, which is what in the secret spanning service is what monitors for any confidential information or overtly permissive commands to prevent this from happening again. Data manipulation can also result in the AI system providing false predictions. If inaccurate data points are provided to the AI, then the AI can be manipulated into giving false data or incorrect predictions. Fluor's AI policy states that any AI tools must be reviewed and pass the governance process. And prompts typed in should be generic and not identify Fluor as a company or a company Fluor does business with. It also advises to not share confidential, proprietary, sensitive, or information and to not upload documents or drawings into AI. When in doubt of whether or not information should be uploaded, employees should ask a manager or a member of the AI task force. And AI should not be used in technical papers or client deliverables that could create, or anything that could create a liability for the company. And human oversight is required for any results produced. I'll now turn the floor over to Phuc to begin the main presentation.
Thank you, Caroline, for the relevant safety topic. A quick agenda for today's presentation. We will be getting into the basic theory of pipeline search, from what is search, to why are we doing the study, then to how we are trying to implement AI and machine learning into our work, our motivation and methodology, our simulation and development process from starting in the simulation model to developing the deep learning machine. From there, we will present our results and findings, as well as some key takeaways for today. To help us better understand what we are trying to do, we need to know what is search. A hydraulic search, or better known as a water hammer, also known as transient pressure, is a pressure shock wave that occurs when the fluid velocity is changed in a pipe. In most cases, for pipeline design, when ignored, water hammer can have severe consequences to operations and safety. Looking at the quick illustration below, the pipes show the pressure profile of the fluid within a pipe when one of its ends is closed rapidly. The wave goes from green to orange, indicating a spike, or otherwise known as surge, within the pipeline. Blue regions are a result of low pressure pockets due to the moving fluid, but in the interest of this study, we will only focus on the extreme pressure surges. It could also be seen with a more complex pipe that the surge pressure can be much higher in magnitude based on the red region. Imagine driving a car at 60 miles per hour, or to the rest of the world, 100 kilometers per hour, and suddenly slamming on the brakes. The results will certainly not be pretty. The car will stop, but your body will keep moving. In a pipeline, since there is nowhere else for the fluid to go, it will start pushing backward onto itself, resulting in the buildup of pressure. Sometimes this buildup can be very extreme. Just to put this into perspective, pipelines often go through many slamming of the brake cycles in operations. Some expected and some aren't. From valve closure, pumps failure, or sudden shift in flow demand. It certainly would be a good idea to ensure this aspect of operations is highly safe and accounted for. Physics-based search calculations are done by the widely accepted Joukowsky equation, where the surge pressure is the result of the incremental spike in pressure with the addition of the initial shutoff pressure. The incremental pressure spike can also be understood as the negative product of the speed of sound or celerity in a fluid with the fluid density and its change in velocity. Usually, this delta V value will be negative, as the final velocity is expected to be zero. Hence, the negative sign in this equation is solely to dictate direction of velocity change. However, Joukowsky is too simplistic and does not account for other influencing factors of the pressure surge. Passing it off to David to further explore this phenomenon.
Thank you, Phuc. Surge events like a fluid hammer and a vapor collapse aren't just theoretical risks. They cause real-world safety incidents and financial losses, especially in complex pipeline networks with varied configurations. But here is the dilemma. Early design stages are when surge risks must be identified, yet this is when we lack detailed data for full transient modeling. Running high-fidelity simulations for every pipe section prohibitively expensive and time-consuming. So engineers rely on simplified tools like the Joukowsky equation, quick this ignores system complexity, leading to unreliable search predictions and band-aid mitigation strategies. Our core question is, how can we rapidly pinpoint search vulnerable zones during conceptual design without costly modeling? We try to bridge the gap with a deep learning tool trained to predict search magnitude and location using physics, not guesswork. Unlike traditional methods, our AI accounts for interactions between critical parameters, such as diameter, valve dynamics, network layout, delivering holistic screening. Now, why distillation? Field search data is near impossible to capture shock waves, evade centers, and measurements are noisy. Instead, we generate high-fidelity simulation data based on hydraulic principles. To train the AI, this avoids data uncertainty while transferring physics-based knowledge. Think of it as teaching the AI where precise digital twins rather than flawed real-world observations. So let's highlight again here. What we mean distillation is that we are transferring knowledge from high-resolution simulations, our teacher, to the lightweight AI model, our student. Again, why simulations? Fluid hammer events last milliseconds. No control system reliably records them. Simulations give us clean, controllable data. Let's validate with a focused case, valve-induced search. We reduce the complexity using two non-dimensional parameters, tau, which is the valve closing time versus sonic wave reflection time, and eta, which is the simulated search pressure versus Joukowsky prediction. Our simulations reveal eta and tau share a polynomial relationship. Crucially, we quantified uncertainty propagation. Variations in tau directly impact eta's reliability, where the equation shown here. This isn't just math. It tells us how confident we can be in AI prediction when real-world inputs are fuzzy. Next steps, scaling this framework to include pumps, network effects, and more parameters. Let's highlight again here our key technical contributions. First is we utilize non-dimensional parameters based on rule of similarity. So we introduce tau, which is non-dimensionalizing valve time that enable us to generalize across pipe length and diameter and the fluid properties. The second is we utilize the Gaussian law on the uncertainty propagation. The Gaussian law shows how input errors propagate, which is vital for judging AI's real-world credibility. Now back to you, Phuc.
Thank you, David, for our motivation and methodology. Next, moving into our simulation and development, going from what we do in the simulation model to how we develop it in our deep learning tool, then to present our findings and validate the accuracy of our machine with uncertainty propagation. Lastly, to describe the study's constraints and set up for our future work. For our simulation modeling, Synergy Pipeline Simulator, or SPS for short, by the company D&V, is the simulation software of this study. SPS is a robust, steady state and transient analysis software for pipeline. It is widely accepted and in many cases preferred within the industry. The depiction shows a very simple and very basic setup within the model. You have an origin or source of fluid connected to a pipeline with a valve at the end of the line leading to the destination as the reservoir or sink. In this study, we consider a typical pipeline with common parameters of design. The pipeline is transporting water with diameter set at 20 inches, length at 20 miles, wall thickness of 0.25 inch, inlet pressure at 750 psig, outlet pressure at 150 psig, because pressure moves from high to low. Material of carbon steel, and the only variable we are considering is the valve closing time. Why? Because Joukowsky doesn't consider a time parameter, which clearly plays a large role in determining the magnitude of the search. A car that has more time to slow down will be much different than a car that has to slam on the brakes. We study 4 types of valves: ball valve, gate valve, linear valve, and globe valve. Why? Each valve has a different opening and closing characteristic, which is the major factor of flow control with respect to time. The steeper the slope, the more aggressive closing of the valve. These 4 valves were chosen based on the most common types of valve in operations. From the simulation, we generated 10,000 data points for each valve for the 4 types, for a total of 40,000 data points. I will now pass it over to Liang for our machine learning development.
Thanks very much, Phuc. So this slide gives an overview of the workflow, showing how we apply an artificial neural network, or ANN, in our study, illustrated here with a detailed logic diagram. So the diagram is divided into 3 key phases. We have training data generation, the ANN model training itself, and uncertainty analysis. So in the first phase, we start by generating input data from a simulation-based model, which serves as a critical input to the neural network. The size and quality of this data sets can directly influence the effectiveness of the model training itself. The second phase shows how the ANN model is built and trained using the input data mentioned by David and Phuc in the previous slide, specifically the valve type and the valve closure time ratio. The model then predicts the surge pressure ratio as an output. Finally, the uncertainty analysis phase demonstrates how the trained model produces error statistics using loss functions. This enables us to evaluate and refine the model effectively, and also supports further uncertainty propagation analysis. Okay, so we've already mentioned the ANN several times, but what exactly is an ANN model? So it is not a new concept. In fact, it has been widely used for many years across the various fields. The model is inspired by the idea that the human brain's functioning can be mimicked by creating the right connections, similar to how biological neurons works in animals and humans. As shown in this slide, the diagram illustrates how a single neuron receives a signal, processes, and then passes it on. So both in biological and artificial context. The artificial neurons follow the same principle. It receives input signals, processes them, and applies different weights to each input before passing the results to the next connected neuron. So now when we talk about the network, we are referring to a system made up of many interconnected artificial neurons. So in a typical AI model, a group of neurons are linked together to form the network. So each connections between the artificial neurons function like a synapse in a biological brain. In the next slide, I will show the actual AI model we used in our study with selected connection highlighted. So this slide provides an overview of the structure of the AI model used in our study. It starts with the input layer, which contains our two neurons, each representing one of our input variables. Next, we have three fully connected dense layers with 64, 32, and 16 neurons respectively. These layers progressively extract features and learn patterns from the input data. Finally, the output layer processes this information to generating the final prediction. The diagrams on the slide visually illustrated these layers and their interconnections, helping to show how data flows through our network. So there are some rule of thumbs methods of determining the size and architecture of the neural network for different applications. However, in practice, selecting the right architecture often comes down to trial and error. Common approach is to begin with a simple model and gradually increase its complexity by adding more and more layers and neurons. So the model's performance is then evaluated using metrics such as mean absolute error, mean square errors, and R-squares. Then the model is built and executed within the TensorFlow environment using Python. The TensorFlow is a powerful open source library that designed for numerical computations and is particularly well suited for machine learning tasks. So while TensorFlow is used here, there's no strict requirement for development environment. So other platforms and tools can also be used, each with their own pros and cons. So as mentioned earlier, the goal of the code is to create, train, and validate the AI model and predict pipeline surge pressure resulting from valve closure events. So before feeding data into the model, it must be pre-processed. The full data set is then randomly split into training, validation, and testing sets to ensure the model can generalize well. To simplify the process of building and training neural network, we use Keras, which is a high-level API built on top of the TensorFlow. The model itself is a multi-layer perception, which is a type of feed-forward neural network. So it consists of an input layer that receives the two features, and followed by the three hidden layers with 64, 32, 16 neurons, respectively, as mentioned in previous slide. And we have a single output neurons that predicts our target. And we also use ReLU, which is called rectified linear unit, as the activation function in the hidden layers. So ReLU introduced a long linearity, enabling the model to learn complex patterns. It enables the model to output 0 for negative inputs and return the input self for positive values. So we also use the Atom optimizer. So it is employed here to adjust the model's weight during training. It's an adaptive learning rate optimization algorithm that typically converges faster and performs better than some of the other traditional methods like stochastic gradient descent, SGD model. So learning rate of the machine learning model is also carefully chosen. If too high, it can prevent convergence, but too low can slow down the training. For the main loss function, we use mean absolute error, MAE, which calculates the average absolute difference between predicted and actual values. MAE is less sensitive to outliers compared to the mean square error, the MSE. However, we also evaluate the model using MSE and R squared to get a more complete picture of the performance. Then, the model is trained over 200 epochs using training datasets, then validated using the validation datasets. Now, note that more epochs can improve learning, however, may also risk overfitting. Finally, the test dataset is used to assess the model's predictive accuracy against the simulation results. An uncertainty analysis is then performed using the trained model, comparing it with the prediction from the valve closure theoretical model. And thank you very much, and I'll pass back to Phuc.
Thank you, Liang, for our AI and machine learning setup. From the training data we generated through our simulation and conversion to unitless pressure and valve closing time ratios, we were able to perform a comparative analysis of our training data with the ANN or AN model predictions. Predictions in yellow indicate that, as you can judge for yourselves, they are quite spot on with very few areas of deviation. With a comparative analysis chart of true values against predictions as direct correlation from the trend line. And results show promising predictions to true values with high precision per initial review. Now, how did we train the model? From the learning improvement chart, an epoch is one complete pass through the entire training data set by the machine or learning algorithm. If you train a model for 10 epochs, it means the model has seen the entire data set 10 times. Since the chart shows the log of the mean square error, learning 200 epochs actually significantly increases the accuracy of the predictions with respect to the simulation or training data. For a log chart, more negative values mean the closer they are to zero, as it actually represents an exponent, not negative errors. And like Liang mentioned earlier, too many epochs, however, is not necessarily advantageous, as it can lead to overfitting and will take up quite an amount of resources, such as power and time. The mean square error, or MSE for short, distribution curve represents the collected error from the model with its probability. Peaks in the curve indicate that MSE values occur more frequently. In this case, the probability of the mean square error being practically zero is very high, indicating the machine can very accurately mimic the simulation. Mean absolute error is the loss function error evaluation, which calculates the average absolute difference between the predicted value and the actual value, which means this metric is less sensitive to outliers compared to MSE. And as seen from the chart, the 40,000 data points have quite low absolute errors and relative distribution, making predicted data highly accurate with training data. But how accurate is the machine? What would happen if we introduce uncertainty within the training data set we are training the model with? How good is it actually? Can we trust our model? In other words, what would happen when we attack the model predictions? Can it still be right when we are wrong? Which brings us to our verification process of our model, the uncertainty propagation. In this case, we arbitrarily pick the globe valve as our subject, and just to define them again, on our right-hand side, we display our uncertainty correlation of the eta, or pressure ratio, with respect to the changing tau, or valve closing time ratio. Furthermore, the relationship of how uncertainty in the input variable, tau, affects the uncertainty in the output variable, eta, giving us a better understanding of our sensitivity analysis and uncertainty quantification. As most of you would expect, our predictions became uncertain as well. In the simulation data, we saw that with uncertainty in tau, eta's deviation also increases as tau increases, noted by the vertical ranges in the chart. Now, how did this affect the AI model? Well, not surprisingly, the uncertainty from the predictions increases. But surprisingly, they are constant at around 1.98%, even with increasing tau values. Another behavior to note with eta distribution is as tau increases, the probability of eta being the same value also changes. At tau equals 0.6, eta is expected to be around 0.74, while at tau equals 1.85, eta is expected to be around 0.72. And tau equals 2.6, eta is expected to be 0.7. This is actually quite critical, as even with uncertainty introduced, the AI model can still pick up the fundamental of with increasing tau, eta should also decrease. Going back to a car slowing down with more time than a car that doesn't scenario. It can be noticed that the probability peaks of eta are shifting to the left, or decreasing as tau increases, similar to what we observe in the simulation data with the downward trend line. So, in a way, the model is still learning and can be fundamentally correct even when we feed it data that includes uncertainty. Although show promising predictions, this study only considered one changing parameters in a list of many. That is, it only considered the valve closing times. Future studies are to be done to refine and develop the model. From our search parameters, there are many more variables to consider. Even more valve types to be tested, a wider range of valve closing times with different pipeline lengths, pipeline diameter, both OD and ID, pipe roughness, complex network or geometry, Reynolds number regarding the flow velocity, and a different type of fluid than water. Beyond that, on our machine learning training domain, our study was done on the very humble machines being used to tune into this webinar today. So there are a few restraints to the computational capacity in regard to CPU. The sensitivity of the model based on the input data, why and how feed data can influence the final results, whether other optimization algorithms can be used. Number of data points, 40,000 data points is a lot, but it's not a lot for a machine to keep learning. Whether the errors computed are rounded or cumulative errors from varying factors, especially in uncertainty. And last but not least, uncertainty validation. And we have enough confidence in our model. These are some of the questions and concerns to be addressed to keep on developing our study. Well, why is this important? Modern industrial facilities and processes are getting more and more complex by the day. Fluor has taken on many projects that include numerous pipelines, including the Petronas Rapid UIO project in Malaysia, as well as the KNPC MAB2 project in Kuwait. Well, what if the facility calls for 100 pipes, or 1,000 pipes, or more than 10,000 pipes, each carrying different product, each with unique dimensions and operating conditions, each with many controlling valves, all subjected to thorough analysis for compliance. We can now leverage the power of computation and machine learning to have an idea of what to expect, whether a pipeline will even need surge mitigation or not, or which pipeline should require more effort and analysis. The goal is to improve the delivery of our analysis with respect to our time to market and quality. If we can improve our results quality and our methods efficiency, even by 15 or 20%, It would be our own failure not to do so. Finally, we come to our key takeaways. So, what did we gather from this study? We successfully implemented the first iteration of machine learning on search screening. Our machine learning model can predict correlating non-dimensional ratios for search pressure and valve closing time for different types of valves with low deviation. However, some concerns arise when uncertainty is introduced into the model's training dataset, as expected. The model's predictions will also see some uncertainty and accuracy as well. There is much more to be understood on how model algorithm handles uncertainty and the correlation of uncertainty as it influences results, which is not clearly defined mathematically. Our first step of experimenting with machine learning in pipeline work has proven to be quite advantageous using theoretical data. Fluor will continue to develop this as an in-house tool, depending on IT governance review and funding to leverage efficient search screening and our capabilities in the AI and machine learning world. To sum it all up, I will leave you with 2 questions and answers. Can the tool be deployed for project use? Well, not quite. This has not been used commercially yet and won't be for a good while. There's a lot more to be tested and a lot more to be understood based on what we learn. Beyond that, before we even think about deploying the tool, we need to protect and barricade all data it will generate to ensure security and trust. Risk proofing will be a major development that is required in order to maintain integrity and confidentiality. But are we on the way there? We are certainly one step closer to where we want to be. That is all from us from the pipeline department. Thank you everyone today for your time. Now turning it over to Dave for the Q&A.
All right, thank you very much, David, Liang, Phuc, and Caroline. So let's take a moment to address some of the questions that we've received from the audience. And for our audience members dialed in, please make use of the Q&A tab to ask any questions to the presenters. So let's start off with the first one that we have here. David, I'm going to send this one over to you. It's a very generic question to get us kicked off. What were a couple of the main challenges faced during the development of the model? Any thoughts on that, David, you'd like to share?
Yeah, so AI is great. However, the drawback of AI is requirements of tremendous data, and the range of training data affects the AI results. So challenge is in 2 aspects. First one, how to generate tremendous amount of data for AI training. The second issue is how to have a wide range of data sets to make the AI applicable in a wide range of practical conditions. So the way we handle this challenge is to utilize similarity rules in the physics, which is for pipeline flow, there's non-dimensionalized factors such as the Reynolds number and the dimensionless valve closing time we just introduced to correlate the results between the non-dimensional parameters and the non-dimensionalized results. So that will enable us to reduce the requirements of data points and also to generate AI model that can be applicable to a much wider range of operation conditions. So that's the the most important challenge and lessons I learned for this study.
Right. Thank you very much, David. I think you may have answered the second question here in that response. So I'm going to move over to the next question that has come in. And I'm going to pose this one to Liang. Do you plan to further develop the ANN model to integrate with real-time monitoring and control systems for pipeline operations? Would you have any thoughts on that, Liang, please?
Thanks, David. Yeah, it is a very good question, and I believe there's two aspects here. So the first, that we are still in the early stage of developing our model, so we will focus on how to incorporate additional parameters mentioned by Phuc, and if necessary, further optimized our ANN structures, for example, layers, the neurons, connections, our loss functions, learning rates, and so on, or even physical induced neural networks. So the second aspect here is the physical limitation of the sensor itself. As David mentioned, they might have noises, errors, and it's not as accurate as you detect those surge pressure that occurs in very short durations. Also, use of real-time monitoring control system. It is more likely to be used on post-processing after the transient event occurs to validate and refine the model. So it is more likely to be used in a large network where daily operation variations can be predicted. So yes, we can implement this. However, it is not our priority at this moment.
Can I add a little bit on this issue? Right.
Certainly.
So
yes.
Because of the difficulty to capture surge signals, to record them, so to use this tool as an online surge mitigation and monitoring device is not practical in the near future. However, this tool can be used by feeding it with gathering operation data from the SCADA system or DCS system on pressure and flow rate. And this AI model can provide guidance on predicting potential surge concerns in manipulating valves, pumps, and control set points. So that can provide some guidance for operators to avoid surge. So that part, I think, eventually it will be able to be integrated into the control system. Yeah.
All right. Excellent. Thank you both for that. David, since you've got the mic, I'm going to pose this next question from our audience to you. And it is this: is Gaussian law standard for uncertainty across all AI, or just specific systems such as pipelines?
The Gaussian law is universal. To basically, it's based on the Taylor expansion. So perturbation in the input on uncertainty can be estimated using the Gaussian law. So as long as you have a system that's continuous, and you can use that law. And you need to be familiar with the mathematical form of that equation. Otherwise, you will need numerical tools to come up with derivatives. So the answer is yes, it's a very common mathematical way to understand the propagation of errors. However, because it's due to the theory of Taylor expansion, the error percentage, right, the deviation shouldn't be too much. Otherwise, the linear term will not be sufficient. You will need to have nonlinear terms.
Okay, great. Thank you very much, David. So this next question I'm going to send over to Phuc. And I know today that we presented the results of valve closure, and varying the time of valve closure was some of the results we presented and showed in the presentation. So this question sort of builds on that, and I guess it's forward-looking in that sense. So this is the question. Could this process consider other surge situations, such as pump failure? Phuc, any thoughts on that?
So, as we mentioned before, this study only consider one changing variable. We understand that there's many variables that can affect the surge pressure. We studied the valve closing time because based on the Joukowsky equation, it does not consider a time parameter for valve closing operation. Valve closing operation is the most common procedures or most likely case scenario that would happen during operations that we are accounting for. So yes, other surge-induced scenarios such as pump failures or sudden shift in demand will also be considered for future study. As said before, this machine learning or algorithm is not ready to be deployed because we need to keep on testing it with changing parameters. We also concluded a list of parameters that we should consider for future development. So yes, the variables such as lengths, such as diameter, the complex network or geometry, it could go up a hill or stay flat or zigzag. Those kind of variables will be considered to be further studied to build on our machine learning model.
Okay, very well. Liang, I'm going to come to you for this question here. And it is this: how does the fluid type influence the surge? And does a small difference in compressibility matter?
Yes, so it's a very good question. So different fluid types will have different density, viscosity, the bulk modulus of the fluid itself. They primarily influence the wave speed that travels within this fluid in a pipeline. So changing the fluid type, but changing the wave speed and hence changing the surge pressure. Of course, as Phuc mentioned, we will consider a different fluid type in the future as adding another dimension to our machine learning model. But yes, it is an important parameters that can be introduced and has to be looked into this.
I want to add one more thing about this question. The current way we are modeling the system is utilizing tau, which is a non-dimensional valve closing time that already include the influence of pipe length, diameter, and also the wave speed of fluid. So for this particular example, we already considered that. Thank you.
Very good. Thank you very much, David. Liang, I'm going to stick with you on the next question that has come in from our audience. And it is this: can multiple sets of input data be put into the system from a spreadsheet to screen multiple lines at the same time? Any thoughts on that?
Yes. So the machine learning models are based on data availabilities, right? So the more data we have, we can train the data model to recognize and distinguish the different systems. So it doesn't matter whether we examine a multiple line or a single line, as long as we have the available data, the machine learning model can be changed or structured to predict the data accordingly. So the importance is that how are we going to obtain as much data as possible rather than to focus on the machine learning model building itself. So yes, so we can access multi-line, or even the AI model itself can screening hundreds, thousands of lines at once. So that's one of the advantages of using the AI model that helps to speed up the screening.
Okay, very good. Excellent, thank you. This next question, I believe, relates to slide 25. So I'm wondering if we can jump back, please, to slide 25 and show our audience. So the question here, I believe, relates to the numbers in the tables, and it is, what is 5% in uncertainty propagation on this slide? So would someone like to take that question? I know, Phuc, you presented this slide, but Liang, I'll certainly open the floor to you on this, or David. So again, the question is, what is the 5%? I believe the attendee is questioning the 5% column that we're showing on this slide. And could you define that, please?
5% is the uncertainty that we introduce. So we're taking it as deviation from the tau value. So let's say 0.1 tau. It's actually, we fed it not just 0.1 taus. We fed it 0.095 or 0.105 taus. So that's where the 5% deviation comes from. So we want to introduce a range of tau for the machines to pick up on instead of just training the rigid 0.1.
Yeah, that 5% is the standard deviation of tau divided by the mean value of tau. Yeah, it's 1 sigma.
All right, excellent. Thank you both very much for that. Just looking at the time here, and I do want to ensure we do end on time, we do have some more questions from our audience members, and rest assured we will make sure that those get transferred over to the presenters today, and they provide written responses to those questions being posed. But with that, I think that looks like it's about all the time we have for questions today. So thank you again, David, Liang, Phuc, and Caroline, for an informative webinar, I would say, and certainly the time that you've spent both today with us and in preparation for today's event. I'd also like to thank our audience for attending today. It certainly has been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com or following our social media channels using hashtag #InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention, and again, thank you for dialing in today. We will send out a compiled list of the Q&A shortly, along with the notification that the webinar recording is available for replay on fluor.com. If you have any questions or if you require additional information, please email innovation.builders@fluor.com, and someone from our team will certainly get back to you. And finally, from all of us at the Innovation Builders team, have a safe day, and thank you all very much.